Hello folks. Like I said at the beginning of the week, this is going to be a massive week. Dealt with mass all week. And let me do a quick recap here. If I can do it quickly, my son will hit me in the head if I don't do it quickly. Okay, so I got to do it quickly. I guess that after a full week of analysis, we should all know perfectly. If someone asks you, your little kid, he asks you, hey daddy, what is mass? You should be able to tell him, right?
You slap him. Where did you hear those words?
More or less. So let's put the super duper definition of mass so that you really get that under your skin. Here it is. We know that mass is not equal to weight. And if you look it up, you'll find that mass is both a property of a physical body and a measure of its resistance to acceleration. In fact, when you look a little deeper, when you open the onion a little more, you get to the center of the onion, you'll find out that it has at least 7 different aspects of mass. So after, 400 years since Newton, you can take that farther back because he wasn't the guy who invented the word mass, but he just came up with a difference, supposed difference between mass and weight. We can say that no one has any idea what mass is. And that's great because, 99% of, I'd say maybe 50% of mathematical physics has to do with mass and the other 50% with time. So here, mathematical physics is founded on the concept of mass. We don't have any idea what mass is. Now, what do you think of that? And so we get to some of the people today, and they say, oh yeah, we know what mass is. In fact, we gave, Peter Higgs a Nobel Prize for discovering what mass is. And we say, oh, okay, that's good to know. And this is what Mr. Higgs says. He says that Higgs field is an ocean that surrounds us. In other words, it's the ether, rediscovered the ether, and a fish swims in this little ocean, right? So all the particles in your body, if you can possibly visualize this, all the particles in your body are struggling against a little Higgs field in their vicinity. They're all swimming in some kind of lake, and they're pushing up against that, and that's against that lake, against those waters, and that's the famous Higgs field, and that's how you create mass. Okay, so that's the notion that we have. He got a Nobel, I guess, for developing the equations that stand behind this notion of mass. And here we have Mr. Jimmy Baggett, and he says the Higgs field is all around us. Okay, so it's confirmed. We have mathematical physics saying that it's the Higgs field that gives you mass. Okay, so I guess that's straightforward. And he goes a step further, and he says that all this mass really comes down to what it comes down to, and I think he says it here. He says all our particles would become massless if somehow you switch the Higgs field off. When you climb on the scales in the morning, you are weighing the energy content of the gluons locked up inside the protons and neutrons of your body. The gluons are those tiny particles that keep your quarks together. And the quarks are what the protons and neutrons are made of, 3 of them in each case. And he says gluons are massless particles. By the way, he also says that quarks are massless particles. And you say, well, hold it. Here you have massless particles. They become massful. They suddenly acquire mass simply because they swim in the Higgs field. And you say, how did they do that? Well, again, it's the resistance. But what's interesting about it is how they illustrate the gluons holding the quarks together. And this is how they do it, okay? And you keep an eye on this one. They put a corkscrew or a bed spring between the particles. As you can see, all the illustrations show that the quarks, those little round circles, the U, the D, and the D, that's the up quark and the down quark. And all these quarks, these three quarks that comprise a proton and the three quarks that comprise a neutron, they're held together by quarks. But the quarks are not little particles like I illustrated on the right. They are a corkscrew. That's how they illustrate them. And that's cheating, I'm saying, because, you know, the corkscrew is not in the standard model of particles. Yeah, I don't know. Is that supposed to be a wave? What is that supposed to be? But that's how they always draw it. And it gives you the misleading impression that these things are held together constantly because there's some kind of bed spring that connects them. When in reality, a gluon is supposed to be a particle, a discrete particle according to a standard model, and it should look like the one on the right. All these quarks are throwing gluon balls at each other. And then, of course, the question is the next one down, and that's, how does a particle pull on another particle? How do you do this? And that's what quantum will never be able to answer. Okay? That's on one side. And on the other side, we had, later on in the week, we had Mr. Einstein, and he says that if you take gravitational mass, and that's when you fall to Earth, it's equal to inertial mass, which is when you are accelerated artificially. So if you're out in space and with your little rocket and you turn the boosters on, you will be flattened against your seat, and that's going to be inertial mass. On the other hand, if you're just falling to Earth, it's the gravitation of Earth. Whatever gravitation is, the Earth just pulling on one mass, pulling on another mass, and you fall to Earth. And Mr. Einstein says those two are equivalent. Now, we don't have a problem with him saying that they're mathematically equivalent. They have the same units, the same magnitudes. I'm having a problem with him saying that this is physically the same thing. In other words, that gravitational mass is physically the same thing as inertial mass. Now, from this, Mr. Einstein concluded that light bends. Okay, and he was able to predict that if you accelerate, like in an elevator, light will bend. That's what that was his theory, and that's what he predicted. And that was later confirmed, allegedly, by Mr. Arthur Eddington in 1919. He saw light coming from around the sun, and he said, oh, see, the gravity well of the sun is warping light from a distant star, and that's why it comes to your eyes. Okay, but I've got a different version of Einstein's principle, and it shows here that the little man falling to Earth is falling to Earth only because every atom in his body is connected to every atom that comprises the Earth. And that is a little different than the guy in the rocket who's just being accelerated. There are no, ropes don't have anything to do with that second scenario. The first scenario, every atom of your body is connected to every atom on Earth. And the second one is just you're being accelerated. So I'm saying inertial mass is not the same thing as gravitational mass as far as from a physical point of view, qualitative point of view, okay? And here we have Mr. Richard Muller. He's a professor at Berkeley, and he stands behind me. He says that every atom on Earth is connected to every atom on you, or it's pulling on every atom of you. And the only way we can, and you're pulling on every atom of it. And the question is, you know, how do you do this physically if not through some elongated mediator? And so that's what he didn't draw there. He drew a whole bunch of points indicating atoms, but he's not saying how that little man he's got on the blackboard is connected to every atom on Earth. And how else are we going to interpret this if not through, you know, some kind of elongated object such as a chain, wire, rope, string, or some kind of elongated object that you can think of. Okay, so they have to be connected. And why is all this important? Why is the principle of equivalence important? Because here we have the torus flying in space. NASA says, look, you're an engineer, you're a physicist. You have to design the torus that's going to hold 10,000 people at least in space. Are you going to send all of them to a certain death because you relied on the principle of equivalence? Is there a difference between gravitational mass and inertial mass? One is where all your ropes are connected to every atom on Earth. The other one is simply an artificial acceleration, which is what the torus has. And specifically, I put the question in this manner here. I got the static version of this. As you can see, the little man that's sitting or standing against the rim of the wheel, he's not being pulled by a whole bunch of ropes from the left. He is being pushed by the centrifugal motion of the wheel. And the question is, are those two physically equivalent? Obviously, they're not physically equivalent, but then the second question comes in is, does this affect you physically?
Are there any consequences?
Yeah, are there any physiological or biological consequences as a result that standing on Earth is not the same thing as standing or being pushed against the rim of a rotating object such as the torus? That's the question. Does this mean that maybe over time something happens and you die because you don't have this gravity? I mean, if we don't sleep, right, for example, they say that after a few months you might even die.
Months?
They say that. Or weeks. Yeah, but my point here is that you need to sleep. And we say, well, why do we need to sleep? Well, I don't know why, but we need to sleep, right? And here we have something similar. We say, well, do you need gravity? And you say, well, yeah, I can give you artificial gravity. And you say, well, do I want to buy it? Is this the same thing? And maybe it's not. Maybe there is something there. You're sending this guy out there, and if you know that, or you have this idea, or you believe that the theory is correct, that every atom of this guy is connected to every atom on Earth, and that's gravitational mass, is different than being pushed, then I think you would want to consider that and say, well, I'd better run a test to find out if these two are equivalent out there, out there in space when I send this guy out there, because otherwise you might be sending him to certain death. There won't be many generations. There'll be one generation. That's it. Maybe. I don't know. I'm just speculating that. And here I show what weight is. And again, here you have an illustration of Newton's universal gravitation versus the second law of motion. And Einstein essentially is saying that the inertial mass, the red one on the left, is equal to the gravitational mass on the right. And he says they're equal because, assuming the rocket accelerates at that speed, we have 9.8 meters per second square on both sides, so mathematically they're equivalent, no doubt about it. But if your body is connected to every atom on Earth, the question is, are these the same? And in order to put that also within a certain context, we have what I'm saying here, that the distance traveled, which is what we see in Newton's second law, is not the same thing as the separation between two masses in his universal law. Okay, these two equations have different qualitative notions of distance. One is distance traveled, the other one is separation. And I'm saying those two are different. And so weight is supposedly that right-hand equation there, gravitational mass, the force that you see there equal to the gravitational constant g, mass times mass divided by distance squared. That is the equation for weight. And here we have weight. We have, this is according to this is according to mathematical physics. They explain this saying, look, there's a field around the Earth. As the box approaches the Earth, it changes weight for every centimeter that it goes towards the center of the Earth. So if you just move 1 millimeter in that field towards the Earth, your weight increases. It changes. Okay? So weight is location specific. It is a static concept, and I'm saying that weight is not a force like Newton suggested with his universal equation. Weight is a tension. Weight only has meaning in the context of a specific location. And that's what a field is. Field is, a potential at each point in a region around a celestial object such as, the Earth, in terms of when we talk about gravity. And the final one here I'll put so that I don't bore you too much. Here you see my version of it. We have a box falling to Earth, and what you see is that what changes is the angle in which the ropes come to that object. And I'm saying that you can do it either way, like my son suggested yesterday. You can look at the angles, or you can count the number of ropes. Either way, you end up with...
Count the number of effective ropes.
Okay.
That's why you can't do it either way. There's only one way to do it, people. It's only with angles. Forget any rope counting.
And you can count the number of effective ropes.
It's just a confusing way of saying adding angles.
Yeah, anyways, either way, what we're looking at is every atom in the box is connected to every atom on Earth. Some atoms are behind other atoms, therefore they're not effective ropes.
Oh,
okay.
I had a question about this
Yeah.
picture GIF.
Anyway,
Can you
I'll just wrap that up.
A mathematician take this same GIF and match...
And match what?
Match the gravitational law, Newton's gravitational law, to this mechanic.
Oh yeah, and it does work. Because this box, what you're looking at here on the box, as it falls, not with it, of course.
Same,
that's you're saying. You're saying if there's what you're saying is there a way to turn Newton's law into an angle law instead of a mass law?
I'm sure there is, but it'd be nice if we had a mathematician that could do that.
Yeah, but my issue here is that this is Newton's law anyways, one way or the other, because you have a distance between the two masses, the box and the Earth in this case, and it's a function of distance. The closer it is to Earth, the more it weighs, and that's exactly what Newton's equation suggests.
But do the angles get smaller at an increasing rate, just like gravity? The further the box is, does the gravitational pull go down exponentially?
Yeah, it does. It does, because you have this situation where the angles...
Exponential?
It is as a function of distance. I think you can show that mathematically. Yeah, I haven't done it, but you could show that the angles, as the as the rocket leaves the Earth, right, as it's flying out, the ropes come together, so the angles, get I guess
you're saying
longer.
You're saying the angles hit zero faster. The further away it is.
Yeah, and it's a square of the distance function. Okay, it's a square of the distance function, to the point where, well, we know this from the pioneers, that at some point, at least the pioneers showed this, and that's both 10 and 11. They both showed that when the pioneers are very far away, very, very far away from the sun, they run into a little bit of a problem. And what is the problem? The problem is that they start slowing down. They're accelerating towards the sun. And you say, how can that be? Why doesn't it continue doing Newton? I mean, it should be going at the same rate as Newton suggested in his equation. I'm saying they entered the bird's beak, from the bird's beak, which is the square of the distance function part of Newton's equation. They entered the linear region where, the coaxials are essentially in a straight line, and there's no acceleration, there's no pull or even a push for that matter. It just drifts at the speed it was going, but now it doesn't have the pull that it had, using Newton's equation. So when it enters the linear region, it's like hitting a brick wall. It's like, here you're calculating everything within the bird's beak, and suddenly, it slows down. Because for the rest of its itinerary, like if the probes were going directly to Alpha Centauri, our nearest star, it's going to go most of the way through the linear region. And in that region, there is essentially no gravity, no acceleration of gravity. Alpha Centauri is not going to pull on it exponentially like, in the bird's beak region near the sun. And so that's what changes. And again, the Pioneer probes, I think, also confirm that that's what we have out there physically. Forget about the mathematics of it. That's what we have out there.
Oh, I found out one more interesting thing about the torus.
Mm-hmm.
I mean, I didn't look it up, but just logically.
Yeah.
things weigh higher, the higher they. Sorry, the things weigh less, the higher up they are in the torus. So if you have like a shelf and you put books up on the shelf, those books weigh less than the books on the floor.
Hold it, but are we talking about perpendicular to the hub?
Towards the hub.
Okay, so
That's
yeah,
up.
okay, so let's get that right. So I'm standing on the rim.
Yeah.
And the book that's closer above my head, which is closer to the hub.
The higher that you stack things, the less they weigh.
Yeah, because you create this artificial gravity, which is also, I would assume, because the closer, like if you were to go around the hub, closer to the hub around, you have almost no gravity. You have to go out there. Yeah, so the distance of the spokes has to be also measured. It's got to be.
I'm just saying that heights are. You have to keep in mind that heights are way. If I go on the roof of this building, I barely feel anything because the Earth is so big that the distance didn't really change so much in respect.
Right.
But on the torus, height is.
Yeah, you only have 170 meters, I think.
Height is very accentuated. So if you got, hell, even a tall guy probably doesn't weigh the same as the short guy.
I hope he doesn't.
Because his head is lighter than the other guy's head.
I hope his head not above the level of air, because then he might have a problem there,
Yeah, that's another one of the little details. It's all those details that you think of on.
Yeah, okay, so the issue is, to sum up, gravitational mass and inertial mass are not equivalent physically, qualitatively. Does that make a difference if you have to build a torus and put 10,000 people up there? Will you kill them all?
Jeez,
well, maybe you kill them all. I don't know. You stay for 6 months and you go there and say, I'm going to visit the torus, and you find everybody's dead because gravity worked differently. That's the question. Is it the same? Qualitatively, obviously, it's not the same under the rope model of gravity and light. That's the first issue. And the second issue is, if they're not qualitatively the same, does it have a biological or physiological effect? And that's food for thought.
You want to go on to the core questions?
Yeah, go ahead.
Let's throw some easy ones. How much mass is needed to, quote-unquote, create gravity?
What? Yeah, with 1 gram, you can do
you
it with...
a whole gram?
Yeah, because all you need is mass times mass. As long as the thing has mass, the object has mass. Newton's equation says, you can put an ant against another ant. You say, well, can you really feel that mass? Well, I don't know if you can feel it, but conceptually, one mass should pull on another mass, especially out in space. I take one ant, if one of these, astronaut ants, it's got no antennas. The antennas are inside, And I send these 2 ants out there, and they weigh. What does an ant weigh? Less than a gram.
That's a weird experiment.
Yeah. You take 2 ants, they should pull on each other.
So
no matter
how much mass is needed to create gravity? The answer is any.
That's correct, but I'm saying that's not true either, and I put that in my book. I'm saying you can't create mass between 2 hydrogen atoms. You need at least 3. You can't create gravity. I'm sorry. You can't create gravity unless you have 3 atoms. You can't do it with 2 because all they're doing is standing there. If there's only 2 hydrogen atoms in the universe, all they do is just kind of twirl around each other. Now, would one atom feel the other atom? And I'm saying they would. It's like you're rolling a stick. Does one end of the stick feel the other end of the stick? I'm saying it doesn't. In order to feel gravity, you need at least now 3 atoms, and one pulls on it. And now one guy is pulling against 2, and then you can feel gravity. So to answer the question, any amount of mass or object, whatever you want to say, is not correct to say that you will sense gravity. You need at least 3 atoms to talk about gravity. Hydrogen, yeah. That's the unit of mass, really.
Do all ropes have the same amount of tension under the rope? If you can talk about amount.
Yeah, that's the issue. The issue is, what do we mean by the amount?
Do they all pull on each other the same way?
They pull on each other the same way in the sense that the velocity of light is constant always, and the only thing that changes is frequency in exchange for wavelength and vice versa. Wavelength gets shorter, frequency increases, and vice versa. Does this mean that there is constant tension? I would say that by definition it appears there's constant tension on the rope itself. Forget about the atoms, but the rope itself has a single tension across the universe, because that's what you're talking about is the velocity of light. The only thing that the rope does is just exchange wavelength for frequency.
But then why do things pull on each other? Gravity.
Because now you have, because again, I like to say that it's not pull, because pull is a force. There is tension, but the tension is where? The tension is between the atoms that comprise one object and the atoms that comprise another object. Okay, so the number of ropes is at a given distance. For that only distance gives you weight, and that weight is the tension.
You mean number of effective ropes.
My son always corrects it. He says number of effect. He shouldn't have to.
Precise with your words.
Yeah, but see, when you get to old age, you kind of brush all these things.
The excuses.
And the number of effective ropes, if I have, and see, this is one way you could do it also. Look, here is, you can do both. You can do your angles, and you can do my ropes. You simply determine that this guy has 10 atoms, this guy has, I don't know, 5 atoms. Now you have maybe whatever number of ropes that comes out to. And you say, okay, now I have, or you can even put fewer atoms if it's better for your calculations. And now you can say, okay, if this guy is over here and this guy's this big, right? And they approach, well, what are the angles of the ropes and how many ropes, effective ropes, are there? And you can do that with, if you simply postulate that your two objects have relatively very few atoms.
Well, we can go back to the 3.
You don't need a gazillion ones.
The 3 hydrogen atoms, you can definitely see the differences in angle, because as long as that triangle isn't a perfect 60 degrees,
right,
someone's getting pulled more than the
correct.
Other two.
And you can do that with just 3 atoms.
If one guy's angle is, let's say, 2 degrees, and the other 2 are what would that be? 178 divided by 2, something like that. They're really big. Then the guy
89
really far. That guy's essentially extremely far away.
Yeah, and you can do it both. You can do it, like I said, if you use few atoms for each of your 2 objects.
We just do it with 3 atoms.
No, well,
3 atoms.
Okay.
With a triangle, you can see the angles perfectly.
Yeah, what I'm saying here is, but you won't see effective ropes.
Yeah,
well, you can.
Well, that's why.
No, I do.
Sucks.
I do. No, you can. Look, put your hand in the middle there. Yeah. Okay, there you have effective ropes. You have no gravity. On the other hand, pull on that now into your door. Now you have effective ropes.
Yeah, but
so you can do it also with 3 atoms.
Effective ropes with 3 atoms. When you're talking about just moving an atom slightly, they're still both effective, just less effective. That's why I don't like effective ropes, because you're talking about it's not effective or not effective. It's less effective or more effective. So degrees is a better way of talking about it. When you're talking about things coming closer, it's not that there's more and more effective ropes. That's not even the issue. It could be the same ropes. They're all not lined up with each other. It's
which is effective.
No. They're all effective. They're all effective ropes in the triangle. You have 2 effective ropes pulling on one.
Yeah,
guy.
but see, if
you change the angle from 90 to 60, they're both still effective.
Yeah, if there is an angle, but what I'm saying, if you have 180,
because effective ropes only deals with the extremes. That's the problem. You're only talking about 180s and zeros. That's why I don't like effective ropes. It doesn't talk about the gradient. Again, with the triangle, if you have a triangle, these 2 ropes are still effective. Okay. You just move this a bit. They're both still effective. They're just more effective.
Yeah, but what I'm saying is they're not effective when all 3 are lined up.
Yeah, because you're only taking extreme cases.
Right. No, it's only in the extreme. Case. It's the only. Right. It's the only case.
It's not the only case.
For the 3 atoms, yes.
No.
Yeah, the only case
again,
is
like I just showed
when you have three atoms lined up, completely lined up. You don't have an effective rope. You only have one rope.
I know.
In the other case, you have
what I'm saying is
3
effective
ropes.
ropes only deals with the extremes like that.
Yeah.
It ignores the gradients in between. You're only talking about 180 or 0.
Correct.
But there's other gradients that take into
all
account.
the other cases are non-effective are effective ropes.
Yeah, but you bunch them all in the same thing, and
Yeah.
that isn't the only thing that changes gravity, whether they're effective or not. Degree is changing.
Oh, I see what you're saying. You're saying that with increased angle. I'm not sure if you have 3 atoms. Let's look at that. If you have just 3 atoms, right?
Mm-hmm.
And in that case, you have two. Hold it. Yeah. You have 2 effective ropes. In other words, what he's saying is you got a triangle, right?
You go from 90 degrees to.
Let's see if I can do this with my fingers somehow.
I'll just do it like this.
Yeah, but okay. So you have something like this, right? You have 3. Can you see that triangle there? Okay, so we have a triangle, right? And
atom here,
yeah,
atom here, and atom
one,
here.
Correct. You have these 3 atoms. The question is whether the fact that the angles widen, in other words, if this atom is getting closer to this, if that angle changes the force on that atom that's approaching the other 2. I'm not sure it does.
I think it does.
No.
That's exactly what you're talking about. When you're fanning out,
I think
until it hits that
I think you
180.
need the number of effective ropes. I don't think you can use just the angle.
No, that's how things work. If
Okay, we got to fight this out. Give us a minute. We're going
back
to.
with black eyes. Okay, next.
That's
next
something
core
we gotta
question.
think about. We're brainstorming here out loud, so it's better to take that offline. We got to look at that. I'm not sure what answer to give that. It just intuitively to me it seems like the angle alone may not be sufficient,
Well,
but I don't know. This is just yeah. I got to think about
Next
that.
core question.
Okay.
What is the smallest theoretical? What is the smallest theoretically possible mass under known physics?
Well, the theoretically or empirically, because
Under known physics, so.
yeah, but I mean the question is there's 2 things. One is the atom smashers that they have like CERN and SLAC and Fermilab and so on. They smash atoms, or particles. They allegedly accelerate protons, and they smash them. They try to find out in their chamber, what debris comes out of that collision, and they look at them and they say, okay, now we have here a subatomic particle, and they come up with at least 200 of them. They come up with quarks and gluons and all these names they give all these little particles. And so you can say, well, obviously a quark is smaller than a proton because the proton is made of quarks. And then the gluon, hopefully, or it seems like, they never said so, but I guess from a conceptual point of view, it has to be smaller than the quark because you have all these gluons going between the quarks holding them together, allegedly, right? And so now we have, the proton. It's a big bowling ball. It's made out of 3 smaller tennis balls. Okay, fine. And each tennis ball is throwing marbles at it. That's that's the picture.
None of these are balls, by the way.
Yeah, but they're corkscrews and springs and whatever. But then, I would suspect that as of today, from an empirical point of view, a mathematician would answer and say, oh, the smallest particle we've seen or we've able to detect is a gluon, I would say, because I'm not sure they can tell you what a gluon is made out of.
That's not the theoretically the smallest theoretical mass because that doesn't have mass, right?
Yeah, well, it does have mass when it goes against the field, the Higgs field.
Oh, okay.
But when it's standing still, it doesn't. But fortunately, all these gluons are constantly hitting the swimming in the Higgs ether, and that's how they acquire mass. But see, they have a contradiction there as well. And let me tell you where the contradiction is. In order to accelerate a particle, they use electron volts, giga electron volts, and even higher. So we're talking about billions of electron volts. What is that? That's a unit of energy. So you need so much energy to accelerate a particle. The smaller the particle, the more energy you need to get it to move along. So what is the energy of a quark? What is the energy of a gluon? What is the energy of a proton? Well, the smaller the particle, the higher the energy. the higher the energy, the more mass it has. And we end up with a gluon having more mass than the entire gold atom. Let me repeat that just in case. The bigger the particle, the smaller the energy you need to accelerate it. But the acceleration energy is a function of the mass of the part. They when they have to transcribe it for their reports, they say, look, we needed so much energy to accelerate a proton, but we needed more energy to accelerate a quark. So the quark has more energy than the proton. What is energy? Energy is mass, right? Under Einstein's E equals mc squared, energy is equal to mass. And so smaller particles have more mass than the bigger particles which they constitute.
See, this is why I prefer to hear this from the horse's mouth. Because when you say it, it sounds like you're building a straw man argument.
I'm not building a straw man. Believe me. Believe me. Look, there's a paper signed. I don't remember the paper now, but I quoted it. I've got it quoted in several places. 50 people signed that paper. They're all mathematicians. And mathematicians. I'm sorry, I said it wrong. And they said that, what was it? I think the quark or the gluon or the, I can't remember which one right now, has more mass, has so much mass. Turns out that mass is greater than the entire gold atom that they squashed together. And you say, hold it, what do you mean? How can this little particle, which is a constituent, the chair, which is the constituent of the house, how can the chair weigh more than the house, including the chair?
Yeah, you're saying the seed of the apple weighs more than the whole apple.
The seed of the apple weighs more than the apple. How can that possibly be? And the reason they reach these conclusions is they need more energy to accelerate the seed than they need to accelerate the apple. And so when they translate into that energy that they need to accelerate it into mass, they end up with saying, well, the seed has more mass than the apple. And you say, how can that possibly be? Because it's a contradiction.
But they couldn't go with any other reason why they would need more energy to move the quark? Why did they jump straight to mass? Like that's the only answer.
Because that is the only answer from a mathematical point of view. You got to accept it because that's mathematics. E equals mc squared. Energy is another. Energy is a different form of mass. That's all it is. So whenever you talk about energy, you're talking about mass. And so the question is how can that possibly be? How can the seed weigh more than the apple? And they say, well, you're not talking about weight. Now you're talking about acceleration. And that's when we get back to, what is mass and what is weight? Are we talking about the quantity of matter that the seed has? Or are we talking about, look, this is how much energy, how much muscle I need to accelerate it? That's what they're dealing with. And that's where I think they run around in circles, because mathematics, because it uses these undefined terms, you end up with such contradictions. I'm sure Newton would have been horrified to find out what became of his equations, how they use them today.
Is there a mass so large that it is immovable?
Yeah, it's called an elephant. I can't move an elephant. Now, can you move the Earth? Well, the Earth is already moving. Fortunately, we don't have to move it. Can you move the sun? The sun is already moving. It's also moving around, the galaxy. Is the galaxy moving? It's moving around other galaxies. So as far as I know, all the masses in the universe are moving around, and so we don't have to worry about moving them. They're already moving. God did that.
I thought you were going to say...
Is that a good answer?
Well, your one from last week was way better. Mm-hmm. If I move, it moves.
Yeah, obviously that's true too. Here's God.
Is there a mass so
here's
large
God, and you say, God.
Is there a mass so large that it is immovable?
Well,
by definition, no, because if I move, I'm moving. It's
right.
In relation to me.
Right. God says, look, I'm not going to move. I'm not going to let anybody move me. And all I have to do is move my little pinky, and God moved with respect to my pinky. So, God can't avoid me moving him, because all I have to do is move my little pinky, and God moved with respect to my pinky. So no matter how powerful he is, he can't stand still in my presence, not when I don't want to.
Does the mass of the Earth ever change?
Yeah, I would think it does, because there's also always some
give and take.
No, imagine, just take this for example, just one quick example. a rocket leaves the Earth. That was mass that belonged to the Earth, and now it's outside. We don't consider it part of the mass of the Earth. The Earth lost mass. Likewise, an asteroid can fall on Earth, and now it contributes to more mass. So you can lose and gain mass depending on whether the asteroid's coming in or smash so much matter that the matter gets thrown out. So in that sense, you can lose mass.
But barring extraterrestrial incursions by humans, does the Earth lose mass?
I would say the mass is constant because the atoms have no place to go.
But we're not talking about atoms exclusively.
Well, that is mass, the number of atoms.
We're also talking about rope because...
that's what I'm saying. The number of atoms should remain the same if there's no outside interference.
But what about amount of rope?
It should remain the same as well because all you have is a conversion of maybe, let's just assume there's a combination of two gases. The number of ropes remains the same. What you do is maybe form a molecule, or even if you did some fusion, let's say there's some fusion going on in the center of the Earth for some reason. The pressures are so great that two atoms get smashed together. So you create a higher element. Let's say you went from lead to uranium somewhere in the center of the Earth. Let's say there's enough pressure. There's no such thing, but let's assume that's the case. Well, still, the lead that turned into uranium inside the center of the Earth, all we're doing under the rope model is putting, more balloons, like the clown in the circus, he gets all these balloons, puts them together.
I think turned into uranium is the wrong way of speaking about it. It's more like it fused with another one.
And turned into...
And we called that amalgamation.
Right, correct. But the number of balloons, if we talk about the unit balloon, which is the atom, the hydrogen atom, remains constant, I would say. I don't think that would change at all.
Is it then safe to say, since I think we're gaining atoms from the sun? I don't know if we get helium or hydrogen atoms from the sun, or if we just get it in the form of energy, rope torsion.
Rope torsion we receive, but that's only influence. That's only motion, energy, through the ropes. So there's no increase in mass in that case. But as far as I know, I can't imagine that would increase the mass of the Earth. So you do get more energy, but not more mass. In order to get more mass, you would need to get more atoms. Now, there is the solar wind. That's a separate issue. But again, we have this protective shield called the magnetosphere that covers the Earth and protects us from the evil forces of the sun.
So kind of in a jiffy to say we're not gaining or losing any mass.
I don't think we are. I'd have to, maybe think about other scenarios where there could be something. Maybe some of these bright folks here might have an idea. Here's Thomas. Let's see what he said. Solar wind blasts off bits of Earth atmosphere. Yeah, it's possible, Tom. I think it's very likely that that's what happens. The solar wind. But keep in mind that, again, we have that protective shield, the magnetosphere, and that's got to be looked into as well. We have a protective shield. And I don't know if that protects us completely,
Next core question is, if light does not have mass, then how can it be absorbed by a black hole?
If light
does not have mass, photons, then how can it be absorbed by a black hole? What answer do physicists give that question?
First, let me use that same question to answer the previous question, because that's important. Mm-hmm. And that's, does the sun contribute more mass on Earth because it sends energy to us? Energy is mass, mass is energy, right? So if the sun throws energy to the Earth every second, to every atom on Earth, it shines on you and throws all these high frequency energy. Why don't we have more mass? The mass should be increased every day, every second of the day, simply by the energy that's coming from the sun. We don't give we don't give energy to the sun. The sun gives energy to us.
We bank it.
Yeah, we absorb all this energy from the sun. Where does it go? Doesn't it turn into mass? If energy is mass and mass is energy, we should be increasing in mass every day.
Like a balloon.
And yeah, and here we have a little contradiction in again, qualitative stuff that mathematics runs over with their steamroller. We got a problem there. And now let's get back to your question. Yeah.
If light does not have mass, then
Yeah.
how can it be absorbed by a black hole? Because they say that black holes don't even let light escape.
Yeah, and
But light doesn't have mass, so how can it be pulled?
light has no inertial mass, no rest mass. It has dynamic. It has relativistic mass.
So when you throw light, it hits you in the face.
No. When a little photon is standing still,
Yeah.
and we measure it, it has no weight. But when it starts moving, it has weight.
So it gets pulled in by the black hole if it starts moving, like the ghost from Mario, where when you look at it, it stops, and then when you look away, it comes towards you.
Yeah, that's called the uncertainty principle. It only does it when you're not when you look at it, because when you look at it, you're hitting it with a photon and moving it.
That's so weird. Okay.
Yeah, so it's like you can't measure the electron or the photon because you need electrons and photons to look at an electron. And by default you're hitting that little particle away. That's their answer.
What does the atomic mass represent?
Atomic. Well, you got atomic number and you got the atomic mass.
What does that represent?
No, let's see if I get that right. It's been such a long time. Atomic number is the number of electrons or protons in an atom, in an element, right? Whereas atomic mass includes all the neutrons that specific type of atom, that specific type of element might have. And you have elements that have, when you find them in nature, some have more neutrons than that same element.
Isotopes.
Yeah, it's the isotopes. And what they do, they take an average of that and say, look, the average, it's a, what do you call it? A weight average, where you take, okay, how many of this atom of this element do we have? Well, there's 90% of these and 10% of these. So they take a weighted average of all that and they say that's the atomic mass of that element. But again, it's a number that gives you an idea of what you can expect in nature empirically if you just take an element at random, whatever, lead or iron or whatever. But again, you got to keep that in mind, that iron is still, according to them, right, has a certain number of protons, a certain number of neutrons, and what changes is only the neutrons in it.
But what is that mass, according to Orbital Model, for example?
Oh,
what are we talking about? The size of the balloons?
Yeah, in a way, you're saying the following. Under the Orbital Model, you have to look at the orbital model of the atom, because the orbital model of the atom is the number of balloons that atom has, built by the threads that just weave through it. And so if you happen to put another balloon in there, like you happen to convert that atom into a higher element, the next one down in the periodic table, then all you did was, by putting that new balloon in there, you change its shape a little bit, right?
The rest of the balloons kind of move.
Yeah, so you change the shape. That's one issue. That balloon.
The other balloons reorient themselves to make room for it.
And because there's these angles. It's like when the clown ties balloons. It pushes the other guys aside, and this new balloon is in there, and that's something like that. And so, but within the balloons, you have the neutrons, and the neutrons, what they do is they tend to also push, the balloons aside within the atom. And what happens? I explained this with both deuterium and tritium, in that they are isotopes of hydrogen. Hydrogen, basic hydrogen, the one that's throughout the universe, is just proton and neutron, right? So what you have is this, under the Rope model, you just have a balloon enclosing a star, period. We're done. What happens when you get deuterium? Now you get another neutron. And my vision of this is that the neutron, which is a star, right, is now inside it and is pushing the shell of the hydrogen atom. You're squeezing it outwards. You're pushing it outwards, right? Because now you put another star inside there together with a proton, and it's pushing the electron shell casing outwards. What happens when you put another neutron? Now you get tritium.
Wait, so you have a proton and 2 neutrons?
First you have one
sorry,
proton
3.
and 1, that's deuterium. Now you put another neutron, you have now 1 proton and 2 neutrons. Now you're pushing that shell, that little shell that the electron is enclosing, now 2 neutrons and 1 proton. Those guys really are pushing that shell to the limit, and that's why tritium is radioactive,
so
because it wants to get rid of that. And it's unstable.
Now
it loses a neutron, and it goes to deuterium. Now it's a little happier than it was before. If you can lose the other neutron, it's happier still and goes back to hydrogen.
So you have 3 converging Urchin stars within this balloon of this electron balloon.
Except that the neutrons are not the same star as the proton. The proton is just threads extending to the shell. These guys are ropes. They're convergence of ropes that are in there.
Oh, okay.
So we have 2 convergence of ropes, the neutrons, together with 1 conversion of threads. Okay, that's the picture. And again, that explains why tritium is unstable, and also why every element above lead is radioactive. They're all trying to get rid of neutrons, and if they could, they would get rid of them, and many of them, I think all of them, convert to lead if left enough time.
Can you talk about like the surface tension of this electron balloon? Because essentially what we're saying is, at some high amount of stars within this balloon, talking about radioactive elements like uranium, if you get enough stars in these balloons, no matter what, after a certain point, the balloons just can't hold X many stars in it.
Right, and you just can't keep feeding neutrons into an atom and hope that it doesn't explode.
Essentially, we're saying the tension, the surface tension, if you can speak about surface tension, of this electron balloon is
at limit, at the max.
No, it's constant. It's always the same, whether it's a hydrogen atom or a uranium atom. But we can see that everything past lead is basically past the surface to what this electron balloon can hold.
Yeah, that's why they're unstable.
Yeah.
The higher elements are, as far as I know, I think anything above lead, I think they're all radioactive.
But why? Because this
of the tension.
Can only hold lead down.
Right.
Well, I mean, there are 2 exceptions. What are they? Technetium, which is 43, and 61 promethium or something. Those 2 are like the odd men in the table where they don't have any stable isotopes.
It's possible. All I'm saying is anything above, what is 84 is lead. Anything above that is, I think all of them are, but maybe not all of them are. But the question is, they're all radioactive.
Even bismuth,
and that's because, the neutrons, if you look at the number of neutrons some of these things have at the higher level, sometimes they're almost twice as much as the protons. So these guys are stuffed with neutrons, and they're sick of it. They really want to get rid of it.
But I would really like for I think the main reason why I'd like the rope model and rope hypothesis to become widespread is so that chemists could tackle it, so that I could finally understand why those 2 elements, technetium and I think it's promethium, this number 61, why are those 2 radioactive? They just seem like 2 odd men out that are under lead, and they have no stable isotopes. Like, why is everything of that guy radioactive? If it's tritium, we're talking about, hydrogen. Yeah,
and it's also unstable.
There are stable hydrogens. There's no stable.
Oh, okay, that's what you're saying.
I'd like to physically. I'd like to see a movie of why that is. Like, what's so special about those 2?
Well, we would see some of these are monsters. When you try to build, I know because I try to do it. I can do easily hydrogen because there's only a little 2 stars and 1 proton.
Baby stuff.
I do baby stuff. I'm not that good at doing things that are heavier than that. But when you get into higher elements, and you get all these protons inside that nucleus, and you try to imagine what this structure looks like with all these shells, the S shells, surrounded by P shells, surrounded by D, and so on down the line, and then surrounded again by S shells, by other P shells. It's a monster. You can't even, you know, it's something that really blows your mind. If you got to be an architect and have a lot of patience to draw these things to find out what they really look like.
That's what I'd love to see.
Yeah.
I want to see a carbon atom.
See what they do, like in the Orbitron, they do look at the shells, and that's good. But see, one of the problems that with the Orbitron model that you'll see on the if you Google Orbitron,
2D?
no, it goes in there, but then see, it doesn't. When it shows, it always shows the outer level. It doesn't show what's in it. And I, you know, so you don't see what's enclosed within that big one. They just show the outer shell, and that's fine. That's pretty good. That's a close approximation. So if you want to know what iron looks like, you just look at the last shell and say, oh, it looks like this. But iron contains, you know, a whole bunch of balloons inside it. It's enclosing balloons. It's enclosing neutrons. And to draw iron, it's got to be a big monster. I don't think you can do that so easily. But in fact, if you wanted to build it with balloons, you know,
like
or well, even if you get the sculptor and you say, look, build this model for me, and you just describe it to him. You say, look, I need a balloon within a balloon within a balloon.
He just says, you don't have enough money, buddy. You can't pay me that much.
The guy says, I don't want to take the job.
I really want to see chemists and I guess 3D modelers or whoever would do that. I really want to see them do an extensive movies out of every atom, just to see why, or have a better idea of why the table of elements isn't symmetrical, like at all. Like it's very messy in there, and you ask, like, wouldn't, you know, Mother Nature, God, the way the universe works, have made that table kind of look symmetrical? Or because if everything's so organized, right, that we can have like tables, you know, bottles, everything seems to make sense to us. Obviously, it's subjective, but you'd think that the table of elements would have been. It looks like ad hoc. Like
God had a headache when he created that. No, but there's another issue, and this is something you got to consider as well. If you look at the Orbitron model that you'll find on the internet, the balloon model, the orbital model, now try to incorporate into that. Now keep this in mind. Try to incorporate within that gluons and quarks running around for every proton and every neutron. Then you will commit suicide, I know. Because if every proton is made out of 3 quarks, and each quark is throwing all these little balls, now try to imagine that, you know, under the current mathematical model, and you'll just go nuts. There's no way, you know, it's just too complex just to do one of those things.
Last question of the day.
Yeah.
Is it true that the equation E equals mc squared means how much energy something has depends on its mass?
Yeah, the equation essentially says mass times velocity of light is equal to energy.
But since the velocity of light is constant, then essentially E is what do you call it? Is correlated to m, on the sense that the more mass something has, the more energy it has.
Yeah, because it's directly proportional, energy to mass. But yeah, again, all they said is that love is equal to intelligence times the velocity of light squared. All we're saying is one concept is equal to another concept. When you look up these two concepts, nobody knows what energy is, nobody knows what mass is. And so what are we talking about? We're done, you know. I mean, unless they define these terms and don't have 7 different definitions for mass, and no definition, or also, you know, there's all kinds of energies out there. There's potential energy and kinetic energy, and they have all these energy, gravitational energy. They have all these energies, and we have all these definitions for energy or notions, and we have all these notions for mass. And what the hell are we talking about?
It gets very meaningless very fast.
Yeah, because they don't have a definition. They can't tell you, look, mass is this, period. They can't do that.
What is equal to mass squared?
Right.
Or energy equals what times c squared?
Right. All we have are letters. The letter E is equal to the letter m times velocity of light squared. What does that mean? We don't know, because we don't know what the E means or what the m means. And so, you know, this week, the m part of it, the mass part of it, we reach a conclusion we don't know what mass is. And that's why we don't use it in science. We have no use for mass or for weight, for that matter. All we do is try to figure out what is happening out there with Mother Nature. What is she doing? She doesn't, you know, I explained in one of the articles this week that Mother Nature doesn't go to college. She doesn't use kilograms. She doesn't know what a kilogram is. She doesn't know what a meter is. She doesn't know what a second is. She only uses objects every day, every minute of the day. And so she doesn't need to go to school to learn how she does her stuff. And we should be like Mother Nature. We should just go out there and do with objects and try to figure out how she's doing her magic with objects, not with math. Because math, again, first has no definitions, and second, even if they were to define these terms, I'm not sure if that would have anything to do with what Mother Nature does out there. And with that, we'll see you next week on Sunday. Same time, same station.